let's talk about linearizations and tangent planes. So first, an example from 17a. Use a linearization of f of x equal to the square root of x to approximate the square root of 39. I'll remind you, the idea behind this is, here's the square root function, and we're going to find the equation of the tangent line at a place that's easy to evaluate. What's a number that's close to 39 that's easy to take the square root of? 36. So let's say this is 36 right here. And what we're going to do is we're going to find the tangent line at that point, 36, 6. And then, to find the square root of 39, well, if I plugged in 39, I would get some value right there, which would come over to be about right there. That would be the actual square root of 9. Instead, what we're going to do is we're going to go up to the linearization, which is a little bit different, and find L of 39, which will be a good approximation. So the way we find the equation of the tangent line, well, you can do all the work and be like, y minus y1 equals, right? So we need two things. I know I didn't finish that sentence there. So we need our function. F of x is the square root of x, or x to the 1/2. And we need the derivative. F prime of x is 1/2 x to the negative 1/2. If you prefer, you can write this as the square root of x. You can write this as 1 over 2 root x. And then we actually need the function value, which is 6, which we already found, right? So f of 36 is square root of 36, which is 6. And we need f prime of 36 to give us the slope. That's going to be 1 over 2 root 36, which is 1 over 2 times 6, which is 1 over 12. So then you can either be like, okay, y minus y1 equals m times x minus x1, and then solve for y, and you get y equal to y1 equal to y equal to y1 plus m times x minus x1. But the way we usually write this when it's a linearization is instead of y, we write L of x. Instead of y1, we write f of a, which is still the y value. And instead of m, we write f prime of a. And we write x minus, instead of x1 and y1, we write a and f of a. We write it like that instead. Where a is the nice convenient value that's easy to evaluate. X is the value that, well, it's actually just the function value. So you could find the linearization at any value. We're going to end up plugging in 39 at the end. And hopefully you can see that all right. It looks kind of small on my screen. So here's my linearization. L of x equals f of a plus f prime of a times x minus a. Sorry, a is 36, not 6. So that's just the equation. I know I used the wrong color or whatever. That's just the equation of this tangent line. And now, if I want to figure out what the square root of 39 is, well, I can approximate the square root of 39 by saying it's the linearization of 39, which is 6 plus 1 over 12 times 39 minus 36. And this simplifies to 6 plus 3 minus 6 is 3, so 3/12. 3/12 is 1/4. So it's 6 plus 1/4. You can either write that as 25/4 or as 6.25. To contrast that, if I look at my calculator here, if I find the square root of 39, I get the square root of 39 because my calculator doesn't want to give me the decimal because this calculator is too smart for its own good. That is interesting. I'll get my other calculator. I'll figure out how to do that later. That's a fun. This calculator is impossible to open. It's gonna look really fun. Oh my god, for real? Sorry, we'll never know. I should say you all should look on your own. So if I turn this on, square root of 39 is 6.24-ish. So good approximation. So square root of 39 is actually about 6.24. So this gives us an approximation of the thing we're trying to find. So all we're really doing is extending this idea to 2 dimensions for when we find a linearization of a function of 2 variables or a tangent plane. Right? So we're basically instead of finding just the tangent line, we're going to find the tangent line in the x direction and the tangent line in the y direction, and then plug in the point we actually want to do to find the approximation. So let's look at this other example here. Time is it? Yeah, I'm alright. So we're going to use linearization, which is a tangent plane, of this function f of x y equal to f 5x squared plus y squared to estimate f of 1.05 2.03. And so here's again the idea. This function, actually we can kind of draw it. This function is a paraboloid. I'm just going to draw something very basic here. And the idea is that, so, right, there's my origin. If this is the y-axis here, and here's the x-axis coming out at us and going away from us, right? Then if I'm at the point 1, 2, so I go 1 for x and 2 for y, so I'm up here kind of like, sorry, this is where the drawing's going to get like a little bit certain. So if x was 1 and y was 2, I get like 7. So I'm saying like maybe up like here. Didn't mean to make that look like it kind of touches there. So this would be the point like say over out 1, over 2, up 7. So there's the point 1, 2, out 1, 2, 9, sorry. X is 1, y is 2, and you get 9. So that's the point that this point is close to, but we're really at f of 1.05, which is a little bit to the right, and y is 2.0, sorry, a little bit out, right? So we're really kind of up a little bit higher than what we'd actually expect. And so the idea here is we're going to find the tangent plane, which maybe kind of looks like that, at that point, where you've got, basically you've got the line in the x direction and the line in the y direction. Again, hopefully you can see that kind of all right. Here's the short answer. So the linearization, now let's make sure I'm writing this the right way. Yeah, I think that's right, yeah. The linearization of x, y is actually very similar to the previous function. I'm gonna write this, I'm gonna go back. It's f of x naught, y naught plus fx evaluated at x naught, y naught. I'm gonna run out of room. I'm gonna write this a little bit lower, sorry. Have L of x, y equals, sorry, f of x naught, y naught plus the partial with respect to x evaluated at the point times x minus x naught plus the partial with respect to y evaluated at x naught, y naught times y minus y naught. This is exactly like the previous version, just the two-dimensional version. So my f of x naught, y naught is like my f of a, my fx of x naught, y naught, my derivative evaluated to the point, is like my f prime of a, and then times x minus x naught is like my x minus a. But we then also have to have it in the y direction. So this piece is exactly the same, it's just here it's the derivative in the y direction times y minus y naught. So it's really just an extension of the linearization formula in one dimension or one variable, but now it's in two variables. So it's actually not too terrible to figure out. Let's do it. So let's find our partials. So first of all, a couple things. So our x naught, y naught, if we look at this, this is not x naught, y naught. X naught is 1, y naught is 2, right? They're the easy values that are close to the values there, and it usually should be pretty obvious. So f of 1, 2 is obviously, I said before, it's 5 plus 4, which is 9. We need fx and fy evaluated here as well. So fx is the partial with respect to x, which is going to be 10x. So fx evaluated at the point 1, 2 is just going to be 10. Fy is going to be 2y. Fy evaluated at the point 1, 2 is going to be, well, I'm plugging in the 2 because I'm plugging in the y, it's going to be 2, which is 4. And then I think that's the whole formula. So here's what my linearization looks like. My linearization at any point xy is f of x naught, y naught, which is f of 1, 2, which is 9, plus fx at x naught, y naught, which was 10, times x minus x naught, and x naught is 1, plus fy, partial with respect to y, which is 4, times y minus the y0 value, which was 2. And then finally, to approximate the function at 1.05 comma 2 point, mother, son of a gun. Sorry, hopefully my screen just started. So my video should be shorter than 10 minutes, otherwise my screen starts to do the, you know what I'm talking about, the screensaver thing? Yeah, screensaver. So to find f of, I should say to approximate f of 1.05 comma 2.03, we're going to plug it into the linearization. Say it's approximately linearization of 1.05 comma 2.03. And then we just plug x equal 1.05 and y equal 2.03. So I'm going to get 9 plus 10 times 1.05 minus 1 is just 0.05 plus 4 times 2.03 minus 2 is just 0.03. So I end up getting 9 plus 10 times 0.05 is 0.5. 4 times 0.03 is 0.12. So you get 9.62. Compared to the actual value, so if you actually plug this in, you get, let's see, so this will work actually, so you get 1.05 squared times 5 plus 2.03 squared, you get 9.6334. So again, a pretty good approximation.